Cool. Thank you so much for the introduction, Jim. This is great. Both Avesh and I are super excited to be here today talking to you all about the Databricks Feature Store, and more specifically, how we went about designing it to work seamlessly with the data and MLOps platforms. So to begin with, Databricks Lakehouse is a platform that is designed to enable organizations to bring in the data into a single data lake built using Delta. And with this architecture, organizations can manage and govern their data into a single place. And this allows users with different personas to interact with a common data platform for a variety of use cases like data engineering, business intelligence, and SQL analytics, and real-time data applications, and of course, data science and machine learning. And to sort of like, complete this, the data platform is available on AWS, Azure, and GCP, and like, wherever your data exists, you can sort of access that and build your data platform. Now, built on top of the Databricks Lakehouse platform, the machine learning functionality enables users to train their models using ML-ready environments and provides several MLOps functionalities like experiment tracking with reproducibility, model understanding, model registry for model lifecycle management, and CI/CD workflows, AutoML functionalities, and then as Jim mentioned, we recently introduced the feature store and feature serving, which was publicly previewed at the Data and AI Summit in May of 2021. Now, the ideation for the Databricks feature store started like most systems at Databricks. We started with talking to exploring the problems in the space and gaps in the industry, and started talking to customers to understand the pain points in their current workflows. Now, dozens of customers that we spoke to covered a wide range of industries, from finance and manufacturing, retail, tech, pharmaceuticals, insurance, and so on and so forth, right? And from all these conversations, we heard commonly recurring themes and very similar problems that data scientists and machine learning engineers were trying to solve. Now, like the first problem that we frequently ran into was the complexity of the end-to-end workflows. And it manifested in a couple of ways. Like in order to solve the problem that they were working on, data scientists wish to have flexibility in the data models of how they organize their data and features. And then most certainly customize the feature computation logic that was best suited for the model architecture. Now, this included using a variety of libraries and frameworks for all stages in the feature computation flow, feature usage flow, and model training flow. And this included things like super complex data types and structures and vectors and maps and so on and so forth. The second thing that we heard most frequently was online-offline skew.
Today's the 13th, correct? Correct.
So the second most frequently problem was the online-offline skew, which is not necessarily specific to the computation logic, but also the data sources that are used and the libraries used in processing. Any slight variation that you have in these in this process and data sources used can have adverse effect on model performance, and this can be very hard to debug. Now, the third thing that we kept hearing over and over again was the need to define the features in a way that can be used for many different projects. Like a new data scientist that may be joining your team, we need to quickly discover all the existing features in the workspace and and quickly start using them for model experimentation, look at the code, how it is used. And then finally, as teams invest in the data computation frameworks and model training and using in their production workflows, they really wanted to avoid proprietary data formats and wanted the ability to access and use these features using any tooling that they are most comfortable using, and most certainly avoid getting locked into a particular vendor. With this in mind, we build the Databricks Feature Store that works closely with the data and ML platforms and enables customers to manage and govern the features pretty much in the same way that you'd expect to manage your models and different workflows, notebooks, and jobs, and even model serving endpoints. I will spend the next few minutes talking about the unique capabilities of the Databricks Feature Store. First is open formats. The system is designed in such a way to enable you to use your favorite framework when you do your computation, and define features using any library and framework, and even simple Python code. Then we standard on Delta as a mechanism to store, which is an open format that to store features in the batch layer. After that, we built a series of low-level APIs to enable access to your features, ETLing the features, and using them in model training and batch and online scoring. With each of these steps, we adopted a pluggable interface, such that it empowers the users to use the frameworks and libraries of your choice that is best suited, again, to solve the problem and for the model that you're trying to build, right? And here, the power and flexibility of MLflow help us achieve that, such that you can use any framework for model scoring, training, and then again, any sort of online serving system for using the features for online model serving. The second strong functionality is search and lineage tracking. Now, search, lineage tracking, discoverability are the cornerstone principles in designing the UI. At a glance, you should be able to see all the data sources that are used to compute your features. Be able to click through to a notebook or a production workflow that is consistently writing and periodically writing to your feature table, the health, and monitor the health of that feature table. And then for each feature in a table or in your system, you should be able to see the consumers that are using these features. It could be like a model or a model endpoint or a job or an ETL process that is using this, right? This enables users to quickly and easily find out all the active consumers of a feature, right? We hear this consistently and frequently from our customers that it helps optimize their search space when they're trying to work on a new project and try to pick the features that would be best suited, and what are the features that are best used by other models. Last and not the least is the seamless integration with MLflow. The feature pipelines compute the features and write it directly to the feature store. Now, we designed a model packaging format, was co-designed with MLflow, such that the model knows exactly which features were used in training that model. Now, with that, it enabled us to write simple APIs for scoring in batch and in online mode, such that regardless of the library or the type of architecture or framework that is used for training the model, the scoring APIs can automatically look up the features at the time of scoring that were used and that are required. Now, we designed several feature providers to be able to automatically look up based on the model says I want these features, automatically look up the features from the appropriate feature provider, whether it's batch or any type of online store. This sort of simplifies your client architecture such that the client at the very right of the screen can just talk to whether it's a model endpoint or a model scoring system to automatically look up the features behind the scene. So the client has to just call the feature endpoint or call the feature scoring, and internally the feature store library does the lookup and the joins that are necessary to score the model. With this, I will now invite my colleague Avesh to demo some of this functionality we just talked about right now, and then later both of us will be available to answer any questions you may have.
Great, thank you so much, Manny. So as Jim mentioned initially, my name is Avesh. I'm a founding engineer on the Feature Store team. And now that Manny has given you this overview of the inspiration that led us to create the Feature Store and talked about the high-level functionality that we offer, I wanted to dive kind of deep into the details and walk through an example application that uses the Databricks Feature Store. So for this application, we're going to be using the New York City Yellow Taxi dataset, which many of you are probably familiar with. We're going to start off by doing some featureization. I'm going to write some features to feature tables. As Manny mentioned, these feature tables are backed by the open source storage engine Delta. After that, we're going to walk through the feature store UI that we offer and talk a little bit about feature discovery and about the kinds of metadata that are automatically captured when you write features into our feature store. Then we'll put on our data scientist hats, and we're going to train a model using some of the features that are available in the feature store. We'll log this model to MLflow, which I think many of you have probably used before. At a high level, it's an open source platform for managing the entire machine learning lifecycle. In this case, we're going to register our model to the MLflow model registry. That will give us some model governance features. It'll give us some slightly simplified batch and real-time prediction interfaces. And then with that, we'll show you how batch inference works. And finally, if we still have time, we're going to talk a little bit about online scoring as well. So let's dive into it. Let's start with feature computation. So as mentioned, our input data is the New York City taxi data set. Every row here is a taxi ride. And the variable that we're going to be predicting in this example model is the fare amount. So the features that we're going to compute are in two different feature tables. We have the pickup features generated from this taxi data, which includes features like the number of trips that took place within a 1 hour window starting from this zip code, or the mean fare for those trips. And we also have a second feature table that's computed from the same source, and these are the drop-off features. Now, our featureization code is just down here. And what it's doing at a high level is it's aggregating the input data in order to create a data frame of feature values. In this case, you'll see this is PySpark code, but we could also use regular Python, or we could also use pandas for this. It's agnostic. So walking through this, we can see that we compute a aggregation feature here, which is the count of the number of trips that took place in a 30-minute window. And we have another feature, is weekend, which is actually a user-defined function up here. It's super simple in this example. This is just determining whether a taxi drop-off time took place on a weekend. But you can imagine these UDFs can become pretty complex, and you could have some complicated featureization logic included here. So we can call this drop-off features function and actually take a look at our feature values. So that's what's displayed here, the drop-off features data frame. And we can see that for each drop-off zip code and rounded timestamp, we have the count trips and whether or not the drop-off took place on a weekend. So now that we have our features, let's actually write them to feature store using the create feature table method. We instantiate a feature store client, and then we're going to call create feature table. You provide a name for this feature table, as well as the primary keys. In this case, it's the zip code and the timestamp that identify the rows of this feature table. And then finally, we pass in the actual data frame. So once we call this method, we're going to be able to view this feature table in the feature store UI. So let me switch tabs to that UI, and we can see all the different feature tables that are available in my organization. So let's say I'm searching for this feature table. I've already forgotten what it was called or the names of any of the features, but I do remember that it was generated from the New York City taxi data set. So I could search for NYC taxi here and find all the feature tables that have a data source that was that data set. And sure enough, this is our trip drop-off features. Clicking into this feature table, we can see some basic metadata, like when it was created or when it was last written to. We can see things like the primary keys of this feature table. And oh, sorry, I'm getting a spam call. Let me decline that. Okay, apologize. We can see the primary keys of that feature table, and we can see the data sources. So this was the field that we searched by. What's neat about this is that our code will automatically pick up the data sources for any feature table. So in this case, we computed our feature values using this New York City yellow taxi Delta table, and that becomes the data source for this feature table. So the lineage story includes these data sources. What's the data used to generate these features? But it also includes what are the entities that were used to produce this feature table, and what are the entities that are consuming from this feature table. So that kind of metadata is also tracked automatically. Down in this producers table, we can see there are two producers for this trip drop-off features table. The first one is the fare feature pipeline, which is a recurring job. So every night at midnight PST, this job runs and it keeps our feature values fresh. And we can see that it last ran last night at midnight and it was successful. And then we can also see a second entity which is producing this feature table, and that's our backfill pipeline. So this was a notebook that was run as a one-off sometime last week and backfilled all of the earlier data. So as a data scientist who's deciding whether or not to use features from this table in my model, I can see that this is kept up to date. These features are fresh, and that's a pretty good sign. But the final thing that I might look for is who else is using this model. So to determine that, we can scroll down here to the features section, and we can see that for each of our features, we list the consumers that are using this feature. So for example, the count trips feature is being used by this model, this taxi example fare package. It could also be used by some endpoints, which are live models that are being served, or by some Databricks jobs or some notebooks that are reading from this feature. Now with that, let me switch back to our notebook. And coming back to Earth, we have this UI, we have all this metadata collected automatically, but this is just Delta tables under the hood. The features are just stored in Delta tables. So because of that, in a way, we're standing in the backs of giants, and we can use any of the existing mechanisms that are in place to read from a Delta table. So this includes native Python or Spark, PySpark, Java, Scala, or SQL. So in this example, we're running a SQL query, and we're trying to figure out the number of trips that took place on a weekend versus a weekday. So you can run this query against this feature table, and we can get back the result and see, okay, 23,000 trips took place on a weekday, 8,000 took place on a weekend. Now, of course, we can do more sophisticated work with these features. So let's put on our data scientist hats, and let's train a model using features from the feature store. What we're going to do is we're going to start off with some event data. This is just more taxi data. And we're going to augment that event data with features from the feature store so that we can then train a model on these features. In this diagram, you can see how we're going to pick up these features. So we have our event data, this taxi fare data frame, and we're going to join in two features from the trip pickup features table. We're going to use count trips and mean fare. And the way that we're going to join those is using the pickup zip code and the rounded pickup date time to pull in these features. What we're going to get back afterwards is this training data frame. And this includes all of the feature values that were requested from the feature store, as well as any additional data from this event data frame that we need. So you can see this defined in code right here. What we're doing is we're saying from the pickup features table, we would like mean fare window 1 hour and count trips window 1 hour. And similarly, from the drop-off features table, we would like count trips and drop-off is weekend. So we can take these feature lookup objects and we can create a training data set from them. So down here, we can see the method call. We call feature store client create training set. We pass in our event data, and we pass in a list of all the features that we would like to train on. What we get back is a training set object, and we can transform that into a data frame for model training, which is what we do here. So taking a peek at that data frame, it has data from the event data, like the pickup zip code, the trip distance, but it also has our feature values pulled in from the feature store. And then finally, all the way on the right, we have the fare amount, which is the variable we're trying to predict here. So in this cell, we're going to do some fairly standard machine learning. We'll partition our data into training and test sets. We'll separate our X and our Y. And eventually, we're going to train this light GBM model in order to predict the taxi fare. With that trained model, we can log the model to MLflow using this feature store client method. And this is going to allow us to later reference this model for batch or for real-time inference. That's actually exactly what we're going to do next. So for batch inference, we're going to take another sample of event data, and we're going to score our taxi fare prediction model that we just logged using this event data. So the data that we're pulling in is this new taxi data. And the way that we score the model is by calling this feature store client method score batch. So we pass in an identifier of the model, that's this URI up here, as well as the event data. And what we get back is all of the feature values this model needed, as well as the predictions. So let's take a look at that. The input here is just the raw event data, just the pickup, drop-off times, trip distance. And what we get back from score batch is this wide data frame that includes features like mean fare and also includes the prediction that the model issued for each of these rows. Now, the way that this works under the hood is described in this diagram, where we're basically score batch is taking the event data and it's talking to the model and figuring out which features this model was trained on. It then joins with those features in order to create the inference data frame. Now, this data frame can be consumed by the model. So we apply the model to this data frame and we get back the output, which includes our prediction. Great. So in the last section, I wanted to talk about the parallel journey. So we've talked about the offline use case of score batch. You might use this for maybe doing a batch daily to write predictions for users to a database. You might do this to evaluate model performance, but you also will have some real-time use cases. So for real-time use cases, you need your features to be available in some sort of low latency online store. So the Databricks Feature Store provides a pluggable interface to publish your feature tables from Delta to an online store. You could use one of a whole number of different online stores. And in this case, we're going to use RDS MySQL. And what we're going to do is we'll create this Amazon RDS MySQL spec. Then we're going to call Feature Store client publish table and publish this feature table to this online store. After we make this call, we can see back in our UI for the trip drop-off features table that it has indeed been published to this online store. And that means that now models can start to refer to this feature table for prediction, for real-time prediction. So let me switch tabs. So what I have over here is a model that's been set up to have a serving endpoint. This is our taxi fare prediction model. And on the serving tab, we can see that you can send a post request to this URL and get back the model prediction. So we'll try that using this text box here. I'm going to copy an input example. Great. So what we're going to pass in is just the event data. So the pickup zip code, pickup date time, and so on. We don't actually pass any of the feature values because the model knows to look those up from the online store. So we can send the request and we can see that it gave back a prediction of $22.73 for this taxi ride. Great. So I wanted to jump back to the top here and leave the remaining time for questions. So yeah, please feel free to ask questions either about this demo or about the slides that Manny went over.